Swayam Prabha. Digital India. Educated India.
Okay, hopefully today we will come to the last lecture of radiation. So, already we are past 30 lectures, so it is time to wind up our study of radiation. But I will teach you something which is very important from an engineering point of view, namely how do we how to calculate gas emissivities and absorptivities in a mixture of gases, which is of fundamental engineering interest, right. As you know, mixtures of gases are very important. So, combustion chambers, furnaces and so on. Wherever you burn a hydrocarbon, you get this water vapor and carbon dioxide, and water vapor and carbon dioxide are both radiatively participating, okay, and they interact. So, there will be an overlapping band, you cannot separate out the absorption bands. If you see, we got a sneak peek into what carbon dioxide and water vapor can do when I projected a slide which showed the attenuation of the radiation entering the earth from the outer atmosphere. It is like a Planck, it's like a Planck's distribution for a black body at 5800, then it enters the atmosphere, then it becomes zigzag, it becomes jagged. So, there are various wavelengths of frequency ranges in which carbon dioxide absorbs, water vapor absorbs and all that. So, if you want to do a detailed calculation, you have to solve the equation of transfer for every spectral band, knowing the properties absorptivity and absorptivity and emissivity, which must come from your spectroscope, which must come from molecular spectroscopy, and then solve it band by band or interval by interval. So, it is called a line by line model. I already told you that it is very advanced, it is very time consuming. But for practical purposes, we do not, practicing engineers, or if you want to have a first cut analysis of a or design of a combustion chamber or a furnace and so on, then we do not have to do those detailed calculations. So, we want a simplified approach, what we essentially call as a recipe, a cookbook recipe, okay. So, that we do minimum calculations, we do not do too much of math, we use some tables or charts and arrive quickly at the absorptivities, then get on to our enclosure theory and proceed with the calculations, okay, that is a goal. So, these charts were developed by Hotel. Hotel was a chemical engineer for the H2O and CO2 mixture developed by Hotel, and the Hotel's charts I have given to you for water vapor and carbon dioxide. Okay, these are okay. So, now if you see epsilon g, if you see the epsilon g, that is a gas emissivity, should be a function of what all variables from your study of optical depth instead of, okay, optical depth. So, can we start with mean beam length? Okay, mean beam length. So, epsilon g, why should it vary on optical depth? Epsilon g need not depend, no? Optical depth will decide the absorption, okay. No, that is not possible always, we will see that. So, then this partial pressure of gas, total pressure Why am I writing it's a function of temperature? Because I know that emissivity is a function of temperature, we have done it so many times. Epsilon lambda versus when I give epsilon lambda versus lambda, if I change the temperature, epsilon changes, because the f of 0 to lambda 2 minus f of 0 to lambda 1 changes. So it should be a function of, there is no doubt about this, it should be a function of mean beam length, correct, there is no doubt about it. Now it should be a function of the partial pressure of the gas. What is the concentration of that gas, carbon dioxide, with respect to the total mixture? Then this is the total pressure, and concentration of other gases. Why does the concentration of other gases affect this? Because it is possible that there can be interaction and there can be an overlap band. There could be some band in which more than one gas absorbs and so on. So this is the general functional form of this. Now the total pressure affects the emissivity, because the total pressure also, among other things, what happens, the total pressure also gives you an idea of how much of gas is contained in some particular volume, and then because of that the intermolecular spacing will change, and because of which its capacity to absorb and emit will also change, correct. So first of all, the baseline charts have been developed for a total gas pressure of 1 atmosphere, and then some correction charts are also available which will correct for pressures other than 1 atmosphere. Okay. So once we do a problem, it will be clear. Now Hotel has prepared the chart for this. It will be it's very interesting to note that Hotel was a chemical engineer. Why do you think chemical engineers were interested in this? Of course they are also interested in burning, converting chemical energy into heat and this thing, they are also interested in all. So chemical Hotel prepared this. Hotel has written a very good book, Hotel and Seraphim, Radiative Heat Transfer, 1967. Okay. So he is basically a okay, when was this? Maybe he prepared this in 1945. Even today we are doing, but now see, the whole point is the fluent has stabilized for CFD, ANSYS has stabilized for a finite element analysis, but no software has stabilized for radiation so far. That is why we people are in the business. Once it starts stabilizing, then we have to work on other types of problems. Okay. So since even today not many people want to get into radiation, and then because even if some people have to develop a general purpose tool, there is a big learning curve involved in trying to run the curve and run the tool and all that. Fluent is very easy, it's third day you can start running Fluent, right, CFD software, but this is not like that. Therefore it has not caught on, and as I told you, very few people work on this. Now principally we are considering two gases, as please look at your charts. So we will have both carbon dioxide and water vapor. Now we will start with A. So the emissivity of the carbon dioxide is a function of the product of the partial pressure of carbon dioxide multiplied by the mean beam length and the gas temperature. Okay. So it is like this. So the product of mean beam length, into pressure is given in both FPS units and SI units on this chart. Abhinandan, you have the chart, or I do not have a chart. You can share. Okay. So you can see that it will give you straight away the gas emittance, the maximum is only 0.3. Okay. So the first chart, what you have to do is, suppose I give you two parallel plates, consider yesterday's problem. If I give you two parallel plates, L equal to 1.5 meter, mean beam length is 1.8 into L, okay, into 1.5, you will calculate the Lm. Then if I say that the total pressure, if the total pressure is 2 bar and the mole fraction of carbon dioxide is 0.4, then what is the partial pressure of carbon dioxide? 0.8. So you will multiply 0.8 by that 1.8 into 1.5 and get the PC into Lm. Okay. Now so various curves are available for various values of this parameter, okay, and Tg is the gas temperature, it is given in both Kelvin and Rankine. From this you will straight away read, from this based on these two you will straight away read the value of epsilon c, okay. Now water vapor, in exactly similar procedure you will read the value of emissivity of the water vapor. Now if if the P total is not equal to 1 atmosphere, then we apply correction factors. The correction factors are so these are based on, these are all empirical, right, these charts I think hopefully he must have done a lot of experiments with varying concentrations, he measured all these quantities and put it in the form of charts, right, okay. So what is Pw is the partial pressure of water vapor plus P divided by 2 Pw and Lm. So you can see emissivity of carbon dioxide, correction for the emissivity for pressure other than 1 atmosphere. Emissivity of water vapor, correction for the emissivity of water vapor for pressures other than 1 atmosphere. These two charts will not be used if the total pressure equal to 1 atmosphere, okay. Now, so then there are some cross terms, there are certain spectral bands in which the absorption of both carbon dioxide and water vapor overlap. So we cannot simply add epsilon of carbon dioxide plus epsilon of water vapor, okay. For example, watch this carefully, if you want to get the total emissivity you may be inclined to believe that it will be epsilon of C plus epsilon of W, right. Now this should be valid for 1 atmosphere. For pressure other than 1 atmosphere you would like to believe that it will be Cc into epsilon C plus Cw into epsilon W, correct, but what happens sometimes the sum of these two will exceed 1, then that will be a startling answer, you can't get an emissivity more than 1, that is because you have not taken care of the overlap, there is an overlap band which has to be subtracted, so we have to take care of the overlap, okay. Spectra of okay. Please go to the last page. This delta epsilon is given, 3 charts are given for this delta epsilon. Unfortunately these are available only for 3 values of temperature, okay. Please note that in order to use this chart I have to work out these 2 parameters, partial pressure of water vapor divided by Pw plus Pc, PC plus PW into mean beam length and TG. Okay, do not assume that PW plus PC must be equal to P total. You can also have nitrogen and other things, inert gases which are there in the gas mixture. Now it is available only for 3 temperatures. Suppose I give you a temperature which is in between, so you have to take 2 charts and do a linear interpolation. Are you getting the point? What are the 3 temperatures for which correction is available? 400, 810 and greater than 1200. So if I give you greater than 1200, straight away use the third chart. Suppose I say the gas temperature is 650 or 945, 950 Kelvin, then you are in trouble. Okay, so you have to read from both the charts and interpolate. Okay, so finally epsilon G, yeah. Epsilon of nitrogen is not there, it is not a participating medium. Yeah, it is an inert gas, it does radiately, it does not participate. Okay, in the atmosphere also we do not worry, it is not a greenhouse gas. If you do not believe me, then we will do DDP, you take an enclosure and put nitrogen and we will, okay. So finally we have, I will write it here. Equation number so how many charts will you read to get epsilon G for a pressure other than 1 atmosphere? 5 times you have to read the chart. Once to calculate epsilon C, once to calculate epsilon W, twice to get their corrections, and the 5th time to do the minus delta epsilon. But then in order to use the 5 charts, some painful parameters have to be worked out, that is PC, LM, TG. That is why it is very important that you write down this properly, you can use it in the exam. So far it was all analytical, but there is no other way of teaching this, the only way we cannot integrate and something and show it. This is the only way to solve the problem of gas emissivities in a mixture in a classroom environment. Okay, so it is not very intellectually stimulating, but it works. Why? Which is epsilon W?
Second term, CW into CW.
Yeah. Okay. Now, what is the story for gas absorptivity? We can't use epsilon G is equal to alpha G. Obviously, it is not a grey gas. First of all, it is not only not a grey gas, it is also different spectral bands for absorption and absorption for various frequencies. Therefore, the alpha G has to be worked out. Fortunately for us, the same charts can be used for alpha G, but with a correction. Okay, what is the correction? For the epsilon G, the gas temperature is very important. For the alpha G, the surface temperature will be very important, because it is absorbing, the gas is absorbing from the neighboring surfaces. Okay, so the same charts can be used for evaluating gas absorptivities, but with the following correction. Okay. Let us not use the word correction because already some correction is there, okay. So with the following changes or following modifications. So what do you want to do for a alpha g, alpha c, yeah, please note this. What is Ts? Surface temperature. Okay. Now alpha W do not ask me why this 0.65, 0.5 everything has come, these are all brute force fit after getting the which surface?
Two surfaces will be.
Multiple surfaces are radiating. Then which surface?
Which surface we have to take?
Temperature will
If we take the parallel plates, there will be
Yeah.
one is 1500 and another is 900 Kelvin.
I don't get your point.
Which is the TS?
Of the absorbing surface.
Multiple surfaces.
Then you have to calculate it separately and use it in the radius in the enclosure method. Okay. Now we will start the development because we cannot straight away go to enclosure. It is the temporary radiation is being absorbed by the gas mixture from a particular earth surface. Okay, we can always start only with one surface. Then we have to use a modified enclosure theory and do it. Okay, so that is not a problem. Okay. Now to the power of point this thing where now invariably when we use this we assume that the whole combustion chamber, the furnace is at one temperature, the gas is at one temperature. So these peculiar cases of one wall at 1500, one wall 1000 all that, this will not work. The different wall is at different temperature, then your question will come which TS I should take, then okay, then this will not work. So as a first cut you can take the average temperature something and proceed, but generally in these problems usually all the furnace walls can be at one temperature and so on. This gives an right in IC engine or something, the cylinder walls are at one temperature, the gas is at one temperature, what is the radiation heat transfer which can be used, and this this value will be used in your CFD simulation. This will come as QR, radiative heat flux, in your calculation. Okay, so epsilon so note this down very carefully. So wherever the temperature comes, instead of Tg we will have some which product?
That product.
Yeah, PCLM Ts by Tg. Okay. Ts by Tg is the normalizing factor. Okay, and finally we also have delta epsilon. Delta alpha. Delta alpha is F8 of Lm. Okay. Now which one? Is it there?
Or TS.
Yes, TS is there. The chart has got two, yeah, no TG. So use the same charts, again you have to use the charts 5 times, okay. One to again calculate alpha C, alpha W, but fortunately CC and CW are the same, so that you have to read only once. Calculate these two values, but do not forget to multiply by this Tg by Ts to the power of 0.65, but unfortunately Tg by Ts to the power of 0.45 for alpha W. Get these two correction factors, incorporate them, get this delta alpha, but from my experience for the kind of problems which we are solving, delta epsilon and delta alpha will be usually 0.01, 0.01, 0.002, 0.03 and so on. If you get some 0.1 and this thing, and which makes both epsilon and alpha become negative, then please check your calculation. Please check the band correction. Please check the band correction. Last figure. Nowhere does it exceed 0.05 or 0.6, correct? So the maximum correction can be 0.05 or 0.6. Okay. Agreed? But in the first two charts you can see that the epsilon CO2 can be 0.3 and the epsilon W can be up to 0.7, okay. So please remember the order of magnitude. The delta alpha and delta epsilon will generally be much smaller compared to, but they cannot be ignored, they can be much smaller compared to this epsilon C and epsilon W, right. So things will look very vague and nebulous when we do something like this, but once we solve a problem everything will be clear. So you have two choices. We'll take a problem which is difficult so that the pressure is 2 atmosphere, or you want to solve a problem with pressure 1 atmosphere. Okay, so that we just do one problem and be done with it. Problem number 41. Hopefully this is the last problem for radiation. Problem number 41. A furnace having a spherical cavity, of 0.5 meters diameter, contains a gas mixture at 2 atmosphere. A furnace having a spherical cavity of 0.5 meters diameter contains a gas mixture at 2 atmosphere and 1400 Kelvin. The mixture consists of CO2, with a partial pressure of 0.6 atmosphere, N2 with a partial pressure of 0.9 atmosphere, N2 with a partial pressure of 0.9 atmosphere, and the remaining is water vapor. Okay, and the remaining is water vapor. If the cavity wall is black, what is the cooling rate? What is the cooling rate required to maintain its temperature? What temperature do you want for ease of it should be lower than the gas temperature, isn't it? 1000 is too much. I have put 500 in the problem. Okay, you take 500, some pain is there. At 500 Kelvin, huh? He wants 810 Kelvin. That is too doctored, no? what is the cooling rate required to maintain the temperature at 500 Kelvin? Okay. Now, Pradeep's question, what happens which TS? So I am carefully drafting the problem such that there is only one surface, huh? Okay. The whole spherical cavity is at one temperature, gas is at one temperature. Gas is very hot, wall is cold. So heat transfer is from gas to wall. Okay. Now we have 20 minutes, we can solve this problem. So for the end semester examination, there will be a solid question on this. Bring your charts. 20 minutes, 15 to 20 marks. Okay. Huh? Let's see. You have 18 minutes. You should be able to solve. Okay. Yeah, let it be like this. So what is this R equal to, did I give 0.5 meter? Okay. What is the first step? Mean beam length, very good. First step is mean beam length. 0.65 D, very good, okay. Next step is to write out all those factors, okay. So PC into LM, okay. So for some people, if you feel that this atmosphere meter is not convenient to work with because basically the charts are given in atmosphere feet, you can take 1 meter is 3.3 feet and proceed, but I feel there is no thing, it's not such a great thing. Both are there, right? Then you can, okay, give me the first value, epsilon c. Is that correct? Can you show this? So we have already found out the PC into LM. PC into LM is basically 0.195. It is somewhere here in the middle, okay, and then Tg, what is the temperature? 1500, so it is in this region, okay, 1400, okay, so it is somewhere in this region. What is the answer? 0.13, okay, you got it. then straight away we can get the Cc. So that is a correction factor. For the correction factor you go to this chart, total pressure is 2 atmosphere, okay, and partial pressure Pc into Lm is again 0.191. So what is the correction factor? Wait 1.1 1.2, okay. So Cc equal to, there is nothing great in what I am doing, you have to do it patiently, that is all. You should know how to read the charts. Point, which is point? You are not getting, why, what are you getting? Yeah, I am 0.13, how many of you did not get? Everybody has got. What are you getting? You are not understanding me? See, this is tabulated in terms of Pc into Lm. Please look here. This chart is tabulated in terms of Pc into Lm. Identify the Pc into Lm corresponding to 0.195 atmosphere meter. Follow that line and let it cut with the Tg 1400 Kelvin. Right side ATM meter is also given. Please look at the table chart carefully. No 035. You have to go along that line.
It will meet one line, no? That so many lines are there, no? You have to move along.
That line is going up and down. Do it carefully.
0.13, how will this?
No, 0.1 to 0.2, so many are there, no?
Oh, okay.
Leo, you got it, no? It will come, just. Correction factor is 1.2? Okay. Now,
Follow the degree Rankine curve, not the degree Kelvin.
no.
Kelvin is down. This is Rankine.
Kelvin is there below.
To go along the line.
You got it finally. Do it patiently, you will get it. Don't be in a hurry. Okay. It is not a ill-posed problem. No, I am following 1400 Kelvin, which is the bottom. It is going, that line is going up and down. Do it carefully. Okay. Vikram, is it okay? Now what about PW? What is the partial pressure of water vapor? 0.5. What is this? 0.163. Now, what is the value of epsilon W? 0.1. 1.4, Got it? You got it? Okay, hang on. I worked this problem out. But I took CO2 0.6, N2 is 1 atmosphere and water vapor, remaining water vapor. Just 2 minutes back I deliberately changed it to 0.9. So that is the partial pressure of N2. So my answers will be different. So I got 0.10, so now you are getting 0.1 for it. Okay. Now PC plus What is Pc plus Pw? 1.1. What is this?
P plus only P plus PW. P plus PW.
No, Pc plus Pw I am calculating and keeping it for something else. Okay. Overlap spectra. How much is this? 0.36, huh? Okay, 35. Okay. Then delta epsilon is, get me delta epsilon. So the delta epsilon, no, I didn't do something. What is that correction factor? CW, na? How much was this? 1.7? So the second chart gives the people who are all at sea. First page gives the emittance of carbon dioxide. First page 1A and 1B. 1A gives the emittance of carbon dioxide, 1B gives the correction for carbon dioxide. Page 2A emissivity of water vapor, 2B correction for water vapor. 3A, B, C, delta epsilon and delta alpha for 3 temperatures. Is that clear? Now to calculate for the water vapor, we proceed to chart number 2, page number 2. 2A we already got the value 0.14. Now I am applying the correction factor. Tell me the correction factor. 1.6, okay. 1.57. Okay. Delta epsilon is? Delta epsilon. Delta epsilon you have to interpolate because 500 Kelvin is not there. Attention please. I have not given 500 Kelvin. 500 Kelvin charts are not available for 500 Kelvin. So you just write in the exam charts are available for 400 Kelvin. I am using 400 Kelvin chart, it is okay. Okay, please use the 400 Kelvin chart, don't waste time interpolating, and please use the 400 Kelvin chart. What is the delta epsilon? If it is a 700 or 900, use the 800 chart, but if I give something plumb in the middle like 600, you have to interpolate. Which one? No, Tg is gas temperature.
1400 we have chart.
Okay, no. My funda you can use it for getting the alpha, delta alpha. So this is gas temperature, sorry. So anyway 1400 you can use the chart number 3, correct? You can straight away use the chart number 3. What is the correction? 0.01 something will come, and what is the correction? Tell me the correction. Yeah. So epsilon g huh? 0.03. Okay. Doesn't matter. It should not be 0.3, that's all. So what is epsilon g? You will get around 0.5 or 0.6 when you struggle and all this. What do you get? 0.36, okay. Okay, so it takes 10 minutes, it takes about 10-12 minutes to get the one gas You have not gone to the enclosure problem actually. You first got epsilon g, right? Then you have to get alpha g. Right? Epsilon g is not equal to alpha g, unfortunately. Correct? We are not talking about a single gas, grey gas and all that. Yeah. Now so repeat the procedure for alpha g. Now, but you have to apply the correction Ts by Tg and all that. The two correction factors are the same, right? The Cc and Cw are the same for alpha, but your first we will do the delta alpha, na? Delta alpha, it is based on the delta alpha so in the correction factor, the last three charts, instead of Tg you should assume that the charts are for equivalent surface temperature, right? Please look here, do not say sir the charts are only for Tg, I do not know what is for Ts. We are using the same chart for calculating alpha also. So assume that these three charts for three temperatures, these three temperatures can be the gas temperature or the surface temperature depending on which property you are seeking to evaluate. Okay. Now, how many of you already given up? Huh? Okay. So tell me at least one. Which one? Alpha C. Okay. Is delta alpha 0.005? One more zero. Absolute zero, huh? Okay. Okay, then leave it. Then it's very safe for us. Calculate the other things, alpha C and alpha W. Okay. I think we cannot start conduction tomorrow, but I thought of completing this. So the first 15 minutes we will solve this problem. Keep these values. I do not have these values because I have different numbers in my. We will spend another 10-15 minutes, close this problem, and then we will start conduction. I just have a simple PowerPoint for introduction to conduction. Next week onwards I will go to regular chalk and talk. Whatever PowerPoint I am using in tomorrow's class, it will be available on Moodle. We are not able to use the Moodle too much this semester because anyway it is all very intense. I am not showing any slides, right. Tomorrow introduction to conduction I will show some slides. So we will solve this problem first 15 minutes and then start conduction, okay. Thank you.